So two proportions are two, again, distinct populations. It might be two samples from the same population, but they're treated as different. Well, the population might be adults, but one of them's adults taking this treatment and adults taking a placebo is pretty common. Those are considered two separate populations. That makes sense. Oh, the board's frozen. Okay, thanks. So that's kind of going to be the key thing. Does preschool help? Remember this one from yesterday's video? So we had these two proportions. And what we want to know is, yeah, are they separate populations? Yeah. They're kids that went to preschool and kids that didn't from poor neighborhoods or whatever. Um, and I'm guessing those that went to preschool were a state-sponsored preschool. Like, hey, preschool is available. I'm not sure if it would have been required or so. Why would we want to do this test? So we're looking at this and going, why would we need to know this information? To see if it's worth, as a government, saying, we're going to make kids go to preschool. We're going to start school not at kindergarten, but we're going to start at preschool. And the idea is we're checking if this amount of education, we generally agree that more education promotes a better society, less crime. I'm personally highly in favor of the let's pay for schools instead of jails because the stronger the education, the lower the crime rates are and things. So there's that thought. But you also don't want to pay for it if it's not effective. Or let's pay for schools instead of welfare is the case in this one, what they're testing. Let's help educate people so that they don't need welfare. That's really the goal of what you're comparing here. And you're going, they get 83% and 61%. Why do we want to compare these as proportions instead of numbers? The sample sizes are slightly different is important. It's also that we have, this is a yes, no type of response. You either needed social services or you didn't. That makes sense? So it's not like there's numerical data. It's 38 were yes, 49 were yes. There's not numerical for each person. So that's kind of the idea on the proportions here. So this is your standard deviation formula. That's a little bit ugly, but remember the proportion one was P1 minus P over N. So you're just putting both of them in there. Your calculator is going to do it for you. So I'm showing you the formula. The mean is the difference in proportions. And you're effectively testing. Remember, if you're testing P1 equals P2, what it's going to effectively do is subtract P2 to the other side and get is the difference equal to 0 within sampling variability. So conditions for this test. Two SRSs, just like two sample t-tests. Practice, we use this confident interval when the proportions are at least 10 times as large as the samples. And so remember, so we had 10 times the sample size for. So your other one was NP is greater than or equal to 10 and N1 minus P. So this is going to change here. This is going to be NP1 hat or P. So if you're doing a confidence interval, you have to use P hat. If you're doing a, this is where it gets a little different. If you're doing a t-test, you're going to use your assumed value of P. Okay. Oh, sorry. These aren't 10, they're now 5. When you're doing a 2 sample, it's 5. For that kind of makes sense. So that's the big change in the conditions. It's the only change from the 1 sample to the 2 sample. And you have to check both samples. There will be a little bit of a change when we get to the 2 sample T or 2 proportion Z test. Okay. But for the interval, it's that. So actually running the test, we have H naught colon P1 is equal to P2. HA, we're seeing if preschool helps. So preschool is my P2 group, and I want that proportion to be lower than my P1 group, no preschool. Okay. Step 2, we're willing to treat these as SRSs. I'm not going to write that all out, but we're willing to treat them because they were effectively randomized samples from a group that we think would be reasonably representative of the population. And P hat 1 equals 61, and P hat 2 equals, so no, it doesn't equal 61. That's 12, which is greater than or equal to 5. This one, 61 times 0.0803 equals 61 minus 12 is 49. This one is also greater than or equal to 5. Without having my calculator in front of me, I don't, it's, it's 62 times 0.613, which is greater than or equal to 5.
Why is it just 0.643 or 1 minus? Okay,
I have to do both. So I have to do both cases. The first one is the for case and the against case. Why isn't it 0.0803?
Oh, yeah.
Oh, it's 0.8. Sorry. So yes, it is 0.803. And you have to do all four of them. That makes sense. A lot of the IB test questions won't actually make you check conditions. And there's not a ton of these proportions-y tests. But I think it's fair game, so you need to know it. And like the samples I've seen have mostly been other types of tests. They've either been T or there's a lot of, they seem to use a lot of binomial in the samples I have. Or sometimes Poisson. So now let's actually do it. I think it wanted us to do the confidence interval, so I'm going to do it on the calculator. How to do this? Menu, statistics, confidence intervals. We are going to do a 2 proportion Z interval. Successes. Successes in this case, again, doesn't really mean success, but it's needed social services. So I have to look at my data. What's it say? 49, 61, 38, 62. So 49 here out of 61, 38 out of 62. It is important to not, and I emphasize it's important to not put in proportions there. You have to put the actual numbers, which occasionally you might have to calculate what that number is, because they might give you, here's the proportion we got out of this many. But you have to give the number of successes that proportion, or you will get an answer that doesn't make a whole lot of sense. So my confidence interval. Okay, I'm confident that the difference is between 0.03 and 0.34. So did it make a difference? Yeah, I'm 95% confident that the difference is between 3% and 34%. So yeah, that's a positive difference. Okay. We're not confident it was a big difference. 3% is not a big difference. But there's the likelihood is that it's not on that extreme. It's more likely to be somewhere in the middle. So P diff, ME, I don't know what those mean. But here's your P hat 1, P hat 2, and 1 and 2. Useful things for your confidence interval. Here they show this. They give us this output. And there's your confidence interval in there. This is a piece of kind of old, outdated statistical software. But it's not uncommon for tests to just give you, hey, the statistics software outputted this. Read it. Okay, what does it mean? And so it's good to become familiar with reading lots of different types of statistics software. If you take a statistics class in college, it depends on this university. Some of them will have you use a calculator. A lot of them will give you stats software. And anything you're doing the analysis for, you type into the stats software. Or some of them you just take, they just give you the outputs. And they just like, you could enter this in, but you can just do the output. Excel is fair stats software. But what the big thing Excel, or you can, I mean, you can do it with Google too, because you can output a .xls. Every stats software reads .xls. So you can, if you put your data in .xls, if you get that, you can analyze it with any program, which is convenient. You don't have to enter your data. And if you're doing data for hundreds of people for big tests, it's really helpful. So, significance tests. Here's how this works. Cholesterol and heart attacks. High levels of cholesterol in blood are associated with higher risk of heart attacks. Will using a drug to lower cholesterol reduce heart attacks? The Helsinki Heart Study looked at this question. Middle-aged men were assigned to at random to one of two treatments. 2,051 men took the drug gemfibrozol to reduce their cholesterol levels. A control group of 2,030 men took placebo. During the next 5 years, 56 men in the gemfibrozol group and 84 men in the placebo group had heart attacks. Here are the sample proportions. That is 4.1% of men in the placebo group against about 2.7% of men who took the drug. Is this apparent benefit of gemfibrozol statistically significant? Okay. What we're asking is there a difference? We're not asking, is this the best treatment? What are the side effects? We're not asking, is it worth the cost? We're simply asking, is there a difference? Does it seem to help? Okay. So identify the population of interest and draw the parameters. H naught. P1 equals P2. The gemfibrozol group and the placebo group have effectively the same rates. HA, gemfibrozol was less than P2. Does that make sense for my things? Okay. Now we've got to talk about our conditions on a t-test or a p-test. So our p we are using what's called not p1 hat, but p hat. And p hat is the combined proportion. So we are taking the total number that had heart attacks out of the overall. Because remember we used with our one sample, we used the assumed proportion for this. Well, you have to do N1 P hat with all of these, and these are 1 minus. Notice that these proportions are the same for N1 and N2. With confidence intervals, you do the proportions individually. With t-tests, you have to do the combined proportion.
T-test, so we are doing t-test?
Or z-test, what the proportion z-tests. Two sample tests. They do not, so because of those two assumptions and those conditions, remember z is always a little bit narrower than t. Those two conditions allow us to use z. So that's why you don't do a proportion t-test, because you have the calculation for the sample or for the population standard deviation.
Are we ever gonna need to portion the T tests?
You don't do proportion t-tests, period.
Like,
I don't think they exist. No, it has two sample t-tests, one proportion and two proportion. Both of those are Z.
Oh, I didn't see that. Oh,
There isn't, as far as I know, and I haven't taken every statistics class, you don't do proportion t-tests because remember we have a formula for population standard deviation. So we can do Z. Anytime we can do Z, we do, because it's a little bit more accurate of a test. Okay. It's just a slightly narrower distribution. And since we have a formula to get sigma, not S, to get the actual population one, we're going to use Z.
oh,
Does that make sense? So checking our conditions, we had, well, they never checked the other conditions, but two SRSs. We're definitely willing to accept that these are two SRSs. One that took the drug, one that didn't, of men with high cholesterol. So notice my population isn't just men, it's men with high cholesterol. And this is probably Helsinki is probably Finnish men with high cholesterol. This we might be able to justify this generalizing to a general population of men, but it might be more like white men. Might not be able to generalize this to black men or Hispanic men. Yeah, but maybe we can. Um, okay. These are all five are larger. We've met that. We also can, I think we can safely assume that the populations are more than 10 times my sample sizes. So all three of those conditions, they don't actually show them all here. They just show the calculating one because that's the one that's new. But this is your lovely formula if you wanted to do that, but we don't really want to do that. It's not that bad. You're just plugging in numbers. Yeah, that's our lovely formula had we wanted to use it. But what we really want to do is go to our calculator. Menu, statistics, stats test, two proportion z-test. $56 out of 2051. I think it's 84 out of 2030. I'm going to go ahead and double check that. Yep. My alternative hypothesis, remember, was P1 is less than P2. I get a test statistic. Remember, important too, you don't need to report with the t-tests on your answers. You'd want to give test statistics a t-value, degrees of freedom, and p-value. Well, there's no degrees of freedom on these. Test statistic, my p-value. I'm pretty sure this did reduce the risk of heart attack. That's less than 0.01. So what can I conclude? My final step is make the conclusion in the context of the problem. So I start with my stats conclusion. I'm going to reject H naught and conclude HA.
Oh,
which means at the 0.01 alpha level, or there's a at the 1% level, I am concluding that the drug gemfibrozole did reduce the risk of heart attack in Finnish men with high cholesterol. What I don't know for sure, I'm assuming it's Finnish men. I don't know that that was actually in there, but it's Helsinki, probably. The capital of Finland.
I have a question. Whenever I go to statistics and stat tests and I do the two proportion D test, it always gives me an error.
I'll have to look at yours specifically. Let me finish the lesson and then I'll look at it after.
So, yeah. I don't know why I'm doing this. Well, I'm not gonna.
Don't drink the water. So, the movie, A Civil Action, tells the story of a major legal battle that took place in a small town of Woburn, Massachusetts. The town well that supplied water to East Woburn residents was contaminated by industrial chemicals. During the period that residents drank water from the well, a sample of 414 births showed 16 birth defects. On the west side of Woburn, which the well was not contaminated, apparently, a random sample of 228 babies born during the time revealed three birth defects. The plaintiffs suing the companies responsible for contamination claimed that these data showed that the rate of birth defects was significantly higher in East Woburn, where the contaminated well water was in use. How strong is the evidence supporting this claim? Okay, this seems reasonable to run a proportion Z test, right? Because either birth defect or not birth defect. So here are mine. So this would be the proportion East Woburn of birth defects equals the proportion West Woburn. The proportion East Woburn is greater than West Woburn. So we choose our conditions. I think this is actually census data, but we'd be willing to treat this as an SRS of people that drank this kind of water. Um, the populations, or does it say it might say it's a random sample. I don't remember. Okay, so these are random samples. We can assume the population is at least 10 times the size. Um, it says they are willing to treat them and they are willing to take them as 2 times. So this is our combined proportion. 414 times that's greater than or equal to 5. My West Woburn side, 6.75 is greater than or equal to 5. Good thing it's 5 now, not 10. These are all greater than or equal to 5. So we can proceed with our test. So again, we'll go to our calculator. Statistics, stats tests. 16 out of 441. So it's 414. Okay. And then 3 out of 228. We're looking that P1 was greater. And we get a p-value of 0.034.
Oh, worse.
So test statistic 1.82, p-value 0.034. So we can conclude that the contaminated water led to higher rate of birth defects. at the 5% alpha level, which is generally what will hold up in court. So more than likely, this judge is going to rule that that company that polluted the well is responsible for these birth defects and owes whatever for damages based on this test.
And
And yes, statistics is super applicable. But remember, one of the things that's really important with statistics, are your conditions met? You cannot just run these tests and start making claims if your conditions are not met, if you're not choosing the right test. Okay. And what are we testing? We're testing against the probability that this was just random. There is always a possibility that it was just random. That probability, the p-value of 0.0344, 3.44% chance that it was just random. Pretty likely that it wasn't. The judge will probably make them pay damages. Depending on that p-value might cause the judge to differ how much damages he makes them pay. Like p-values, he's probably going to rule yes. It's not like it was 0.0001. So he might not award as much in damages. But that's your two proportion Z tests. That's it.